Happy spring, by the way. All right, so let's put the quiz on chapter 36 next Monday.
Yeah. 2.
Yes, sir.
So the test correction is due on next Wednesday, right?
Yes, I believe it's at the end of the month.
Yes.
Isn't next weekend? No. What's the weekend after next? Easter.
Huh?
The weekend after next is Easter. Yeah. First weekend of April.
And again, if the test correction is not ready on next Wednesday, then just let me know when I am going to see it. But that's the target date.
I think you're giving me my test spot.
Oh. Oh. Yeah, I need to. If you look in the testing center, I would have a virtual copy of it. So, yeah, you'll email that to you. Did you already send me an email to remind you?
I don't think so. I can send you one today.
I would appreciate that. Any other questions at this point? All right, the three basic properties we talked about when dealing with light in the very beginning of the light chapters, were reflection, refraction, and diffraction. So obviously we've dealt with reflection, we've dealt with refraction, now let's deal with diffraction.
What is this, 36?
37. Yeah, the quiz on 36 is in a week. Chapter 37.
Okay.
Now we've seen some of this already. You've done the vibrating string experiment where you have waves going one way and bouncing back and they interfere with each other. We have the same thing going on here. We have interference patterns. So which leads to diffraction, which ultimately leads to the dark side. Now you can see interference patterns. I think we've done the finger thing. If you look at between the cracks in your fingers and you see those little bands, dark bands in between, especially near where the skins meet. That is a diffraction pattern. That is known as single slit diffraction. So let's talk a little bit behind the math of it. So I have what's called a double slit. And I send light waves towards it. Well, we can actually see what happens when we do this. I'm going to go grab a double slit and release it.
Oh, that's all you want? I think the little guy, maybe. Maybe, I think he passed away. So,
All right, I'll find the nicer ones later. All right, we're gonna need to turn the light out. Pardon?
Something like this.
Something like that.
Easy to come down?
I don't think so, but let's find out. All right, there you go. You see that bright spot in the middle, and then you see there's a dark band, and then you got another, there's another lighter red band just to the left and to the right.
Yep.
I don't see
It's
it.
kind of hard to tell, but I can see it.
All right.
I mean, like,
Yeah, let's kill those. Just. Got the bright spot in the middle, and then you've got a dark spot, bright spot, dark spot.
Oh, yeah, now I'm seeing it.
All right. Actually, if you look closer, you'd see some other marks as well. That each of those bright spots off to the side have dark and bright light bands to them as well. Can you see within? I can't really point.
Like within each.
Yeah, within each of those, you've got, oops, lost it. Within each of those, you've got light and dark bands too.
Yeah.
All right. Not too much retina burn. Count it as a win. Thank you, Holden. And so you got the two different patterns are going on there. One is because of the double slit, one because of the single slit. Now in this particular case, the double slit I was using was a lock of hair. So it's just one strand of hair, and I was shining the beam right on it, and the hair was splitting the beam into two, and that's where you're getting the interference patterns from. If we looked at the patterns a little bit more closely and started marking out how far is it between the really dark bands, so you've got the really dark band here, and then lighter than. If we looked at these distances, actually, the bright spot, we could then come up with an estimate for how wide that hair is. Now, you do have what is known as sort of a light envelope here, and so within this you also have these patterns that are stemming from what is known as single slit diffraction, sort of what you're seeing when you do this, you get the single slit diffraction. Again, we'll get into that. So as the light comes in, it hits the wall, you suddenly, if you think about it in terms of waves, you have the waves coming out. The points where they are overlapping like this, these are two peaks overlapping, and we get constructive interference. This would be the bright spots. And the places where one is peaking, but the other one is troughing, like right here, this would be a dark spot. So this would be dark, and this would be bright. So ultimately we have a screen over here, and so we have some middle spot, so some central. That's where you get the brightest spot right there, because the distance from here to here is the same for both of them. It would definitely be constructive interference, because they are both in phase. Take the spot here. That light coming out of the bottom slit travels that far, pretend that's a straight line, and the light coming from here traveling that far. There is a difference in the distance that the light is traveling. We are assuming that light is traveling at the same speed, that the medium, for instance, the air, was relatively uniform. So let's see if I can actually draw that without a lot of that interference there. So the distance between them is some distance d. See how do I want to split this up? There are a couple different approaches to take on it. How much do I want to subject you to? There's the desire to subject you to more than you probably want. We'll do it the easy way for right now. This distance from here to here, we're going to label it as y. So basically I want a relationship between y and d. So in the case of the example I did just then, d would be the width of the hair. This is some angle theta. This would be some angle theta 1, and this would be some angle theta 2. Now those angles are all roughly the same. I have this light beam that's moving back and forth, one coming from here that's moving back and forth, and what I care about is the difference between them. So if this is some distance r1, and from here to here is r2, r2 is bigger than r1. If I were down here, it'd be the other way around. But if this distance from here to here is r1, in other words, we have an isosceles triangle. The question is this difference in distance. If it's a full wavelength, they'll be in constructive interference. So like one wave doing this, and the other wave. So if it's a full wavelength off, everything's good. If it's a half wavelength off,
That's destructive.
yep. Oh, I'm a little bit off in my drawing there. They cancel each other out. Going to So I want to go to the bright bands. All right, so R2 is R1 plus suddenly my mind is blanking.
What is N? Is that that's the medium it's traveling through?
Oh. No. Oh, no, this is just, let me use a different letter. Yeah. So, if R2 is equal to R1 plus some integer times the wavelength. M is an integer. M is an element of integers. Times the wavelength, then we get a bright band. So let's take a look at this triangle right here. So actually, two triangles I want to look at. I have this triangle right here. And then I have this triangle right here. This is some distance y. This is some angle theta. Now, this is an isosceles triangle. This angle right here this angle right here and this angle right here are equal to each other. However, they're not exactly 90 degrees, but they are close enough. Especially the farther the distance away is. If you think about the example we did just there where we had the width of a human hair and that distance right there, that's pretty darn close to this angle being really darn close to 0 degrees, making those really darn close to 90 degrees. So we are going to make that assumption that that is close enough to 90-degree angle, and that is a 90-degree angle. This angle right here is approximately equal to theta. And so we have similar triangles. If I make the distance from here to the wall L, this here is D. And this is equal to some integer times the wavelength. Well, if we set up this, I know the tangent of theta from this right here is equal to y over L, opposite over adjacent. From the smaller triangle right there, the sine of theta is equal to m lambda over d, d being the width of the hair or the distance between the two slits. And theta is just a pretty darn small number. Oh, wait. Yeah, theta itself is a pretty small angle. So we use the small angle approximation. Y over L is equal to M lambda over D. And so now it comes to what you want to solve for. If we're solving for D, that's going to be M lambda L over Y. And so now we can predict the width of that hair. So let's set that up. Somewhere around here. Clip. And my laser that I had in my hand, I'll put down here. If you could kill the lights, please. All right, so I'm going to take my marker. I'm going to mark the bright spot here. And then I've got the middle of the next bright spot, next bright spot, next bright spot. And is that asymmetric? All right. Lights back on, please. So this is where y is equal to 0, or m is equal to 0. This would be m is equal to 1, 2, 3, and so on, -1, -2, -3, -4, and so on. So m is just how many wavelengths apart are they? Well, on distance here, let me go to the third one. And that is about 6.5 centimeters. So y is 0.065 meters. M is 3. L is the distance from there to here. Since we're doing crude measurements here, that's the meters to there. 2 meters to there. 2.37. This is 2.37 meters. And the wavelength. Well, we have to pull that from the manufacturer. They give us a range. It is red, so that should narrow it down. Or we could just look on the box.
Got 109.38.
All right.
These are the big ones.
All right, and then lambda is about 655 nanometers.
Oh, that's what I was missing. I got 1.43 times 10 to the negative fourth.
And that would be meters.
Meters, yes.
In other words, 0.143 millimeters. And so now the question is, what's the width of human hair? Anyone happen to know? Uh,
180 micrometers.
180?
Yeah.
And we have 143. So we're in the right ballpark. Now, different hair has different widths. I think blonde hair is thinner than.
It says between 17 and 180. So
Okay.
So we're definitely in the ballpark.
All right. I'm going to count that as a win.
It's a little bit thick.
And doesn't it depend on where the hair is on the body?
That's possible. This one would have come from, if it's human hair, actually human hair, that would have come from the head, I assume. And if it's dog hair, who knows?
Yeah, I mean, I was talking human hair, but then again, rather not say.
Looks like there's a slight reddish tinge to it, so that could have been our dog or our daughter's. And my hair hasn't been that color for decades.
Well, it looks like she's part of the. Looks like she was in the video.
That's right.
Part of her was in the video.
Anyway, have a wonderful afternoon. Welcome back. Glad all of you made it.